So this is just kind of a test video I'm doing because I'm trying to turn this channel into a place where I occasionally upload interesting math videos or just math tutorials in general because, you know, I'm trying to get exposure on like explaining certain things so that, you know, I can remember them easier. But for the sake of, you know, just the first video on this channel as like a test, I'm just going to show a pretty simple proof of the quadratic formula, which most of you, if you're watching this, may or may not know how to solve, but I'm just going to show it anyway because, you know, there are tons of videos out on YouTube where they prove this formula, which if you've seen this enough, or if you're at least at middle school, right? You're in like year 9 or year 10 maybe, right? Or you're in like your first year of high school. You've probably seen this formula many times, right? X is equal to negative b plus minus square root of b squared minus 4ac over 2a. I'm just going to show a simple proof of, or just like one of the common proofs as to why this formula is the way it is. But then I'm also going to show an extra application, which is what this thing is, which is called the discriminant. Now, the reason it's called the discriminant is because it discriminates, right? Not in a negative way. It discriminates, or basically distinguishes between different types of roots. Now, you've probably heard common phrases like why, when this is the case, when b squared minus 4ac is greater than 0, will we get two distinct roots? Or if you've seen b squared minus 4ac being equal to 0, you see two equal roots, right? You might be wondering, why is that the case? A lot of people just memorize this, by the way. A lot of people, when they see this, they just memorize, okay, when it's greater than 0, it's distinct roots. When it's equal to 0, it's equal. When it's less than 0, there's no real roots. That's not the way to go about it. I'm just going to show you why it is better to understand this concept of the discriminant from the quadratic formula itself, because it is way easier, right? And also it makes much more sense as to why every case is the way it is. You can't resort to just memorizing each and every case. That's not how you do that in math. You need to understand it, right? And somewhere it's pretty much easier if you understand why each case gives you like a different thing, right? It's not good just memorizing, oh, if it's equal to 0, then this is the type of root you're going to get for your equation. That's not a good way to do it. You have to resort to understanding it if you're going to know how to apply it in multiple different cases, right? So we're going to start proving with the general formula, right? Just start by writing out the general formula. This is the general formula of a quadratic equation. Ax squared plus bx plus c is equal to 0. Pretty standard. If you see this equation, you pretty much know that this is a quadratic equation. We have to apply a special case though, right? The specific constraint or condition that we have is that a is not 0. Because if a is 0, 1, you know, if we see the formula here, that's going to create some problems because we're going to have a division by 0. Nobody wants to divide by 0, right? Secondly, and this makes more sense if you just don't look at a formula, if a was 0, then this would turn into a linear equation. Imagine if this thing was gone and you were left with this. This would just be a linear equation. And, you know, we know how to solve linear equations. So it's not really that interesting anymore. And also, we don't even need the quadratic formula if it wasn't a linear equation. So for the sake of simplicity, we're just going to make sure a is not 0 to make sure that it is a quadratic equation. If b were 0, basically we would just have some ax squared plus c equals 0. That's still a quadratic equation. For example, if you see an equation like x squared plus 4 is equal to 0, this is still a quadratic equation because in this case b is 0, right? But this is still a quadratic equation because we have a power 2, right? As long as there's a power 2 variable in your equation, it's a quadratic equation. Makes sense. So we're going to start by doing what most people do when they try to solve an equation, like a linear equation, which is you would try to isolate the variable, right? You would try to isolate the variable that you're trying to solve for on one side. So what we're going to do is we're going to keep all the x terms, everything with x, on the left-hand side, and then all the non-x terms will go on the right-hand side. So we're going to subtract c from both sides to get this particular equation. But then if we want to do factorization, right, because we're going to have to factorize this in some way where we're going to be left with an x. We don't want this a in the front because this is going to create some problems for us when we try to factorize. So we're going to divide both sides by a to get this new equation, x squared plus b over ax is equal to c over a, negative c over a. So up until this point, this seems pretty standard. But now, what do we have to do to get this part to be x plus something, or x plus something squared, so that when we factorize it and then we square root both sides, we're left with an x on the left-hand side? Well, we're going to have to factorize it in a way using something called completing the square. If you've learned quadratic equations already, or if you haven't, you may remember the binomial expansion, where if you expand a power 2 binomial like this, your result is a squared plus 2ab plus b squared, right? You notice that this particular part, this left-hand side, is something similar to this, right? Where in this case, our a squared is kind of like x squared. But you notice we're missing a few things, like we're missing this b squared. But what's important is that this 2ab is actually represented by this b over ax over here. So if we say that 2ab, or 2 times something times another something, is our b over ax, this would mean that this would be 2 times x, because our a squared is x squared, so our a is x, right? So our a is x times b over something, such that it results in b over ax, and it's in this form. In this case, our b is b over 2a, because simplifying this gets us b over ax, and it's also in this form, 2ab. So our b here in this case, or if you want to write it, you can say p plus q is equal to p squared plus 2pq plus q squared in order to avoid confusion of variables. 2pq is equal to b over ax, which is equal to 2 times x times b over 2a. This is in the form 2pq. Since our p here, or our a, is already x, our b or q here must be this, b over 2a, right? So because that's the case, we can write this as a sort of square. Because if we can reduce this down to just a simple binomial, meaning if we can reduce this down to just a bracket with a square on top and with 2 linear terms inside, then we're good, because that's easy for us to solve. So what we're going to do is we're going to add this b over 2a squared to both sides. Okay, we're going to add this to both sides, and we're going to simplify something. So this left-hand side is essentially in the form this, right? P plus q squared is equal to p squared plus 2pq plus q squared. So our p squared is x squared. Our 2pq is b over ax, because it's 2 times x times this q squared, which is b over 2a squared. So this is in the form of a binomial. So we can factorize it, or rewrite it, as x plus b over 2a squared, as this is a valid factorization of this. On the left-hand side, sorry, on the right-hand side, we can sort of simplify this by opening up the square to get b squared over 4a squared. And then we can combine these two fractions to get negative 4ac plus b squared over 4a squared, right? So far, this is just algebra. I mean, this is algebra. So we have a binomial to the power 2 on the left, and this fraction on the right. And now, if we want to solve for x, we're just going to do simple solving, right? So first off, we're going to take the square root of both sides, because if we want to solve for x, we want to get rid of this square that's bounding our x. So this is actually going to turn into the square root of b squared. I'm just going to rewrite this because this is the same thing. B squared. This is just going to be b squared minus 4ac all right? This is the same thing. I'm just rearranging them over 4a squared. But because we didn't specify if we were taking the positive or negative square root, aka the principal or non-principal square root, we have to specify that we're putting a plus minus here, because the answer could either be positive or negative. Because remember, if x squared is equal to 9, x is not just 3, it's plus minus 3, because you can rearrange this equation into the form x squared minus, x squared minus 9 is equal to 0, which this in and of itself is a quadratic equation, but if you see it, this is actually the difference of two squares, x plus 3, x minus 3, because 9 is the same as 3 squared. So this is a difference of two squares. So if you notice, x can either be negative 3 or 3, because for a quadratic equation, as long as one of these terms is 0, then the whole equation becomes 0, right? So either negative 3 or 3 will make the entire equation 0. So if you notice, the square root of 9, x squared equals 9, x can either be negative 3 or 3, because if you plug either one of these numbers in, you're going to get 9, because a negative number squared is a positive number. So if we're not specifying whether or not the square root we're putting is going to give us a positive or negative answer, we have to denote the fact that it's going to have two possible answers. It's going to be a plus or a minus. To simplify, we're going to rewrite this, because it doesn't matter if we write it on the top or the bottom, it's the same. So we're going to write it on the top as, for convenience sake, this is square root of b squared minus 4ac over the square root of 4a squared, the principal one, is just 2a. And the reason we don't have to put a plus minus here, because the plus minus and this plus minus will, it doesn't make a difference, right? If we put a plus here or a minus here, it's just going to be the same. This is still going to be a plus minus. This, on the other hand, or basically you can say that this is we're taking the principal square root of 4a squared, which is just 2a. So we don't need to worry about negatives. Even if there were negatives, it wouldn't make a difference, because this wouldn't change, right? This wouldn't change. It would still be a plus minus. If it were negative, it wouldn't really make a difference because of the plus minus. This part is still the same. So we can isolate x now by moving or subtracting b over 2a from both sides to get negative b plus minus square root of b squared minus 4ac over 2a. Notice what I did was I basically just put negative b over 2a in front, right? And I combined the two fractions. So all I got was this formula, which is essentially what everybody knows as the quadratic formula. But this has another application. What I mentioned was the discriminant. So the discriminant is essentially the term in this quadratic equation that's under the square root, right? It's this b squared minus 4ac. So we usually denote this as a d. So d is equal to b squared minus 4ac. I'm going to denote it as d from now on to make it easier for me. I don't want to keep writing this. I'd rather write d. So we have actually three different cases of this, where if d is greater than 0, d is equal to 0, and if d is less than 0. This gives us two different or distinct, right? But it means the same thing, right? Basically, they're two different roots. This gives us one real root. Oh, I need to mention, these two roots are real. Right? These two roots are real roots. This one gives us one real root, or you could also say it gives us two equal real roots, right? I'm going to denote this capital R here means real, two equal real roots. This means 0 real roots. But you could also say that these are two complex roots. Complex meaning they are complex numbers, right? Meaning they have those i's in them, which nobody likes, because, nobody likes to see i's in an equation. Right? You learn in the future that these are actually very important, but for now, we just know that they are complex roots, meaning they're not real numbers, right? They don't only have a real component, they have that imaginary component with the I term inside. So why is this the case? Why does this work? Well, look at it from this angle. If d was greater than 0, meaning this term was positive, then the term under the square root would be positive. So if the term under the square root was positive but not 0, right? Let's call whatever number that is k, right? Let's call it k, right? So if d was some k that is greater than 0, we would end up with x being equal to negative b plus minus the square root of k, right? Because we know that this term under the square root is k now, which is greater than 0, and this is over 2a. This gives us two possible roots, negative b plus square root k over 2a, or negative b minus square root k over 2a. That's why it gives us two distinct or different real roots, because this is not 0. Hence, we can get a plus a certain number or minus a certain number. Hence, we will have two different roots. These are called conjugate roots, right? Because the minus equivalent of a plus term, like this, is called the conjugate term, right? What about the case when it is 0? If k was 0 instead, right? K was 0, then this 0 would just be square root of 0 is 0, right? So we would get negative b plus minus 0 over 2a. Well, adding and subtracting 0 is the same thing, right? They're essentially the same thing. So we're gonna be left with one term, negative b over 2a. So negative b over 2a is one root. So this is why we say we have either one real root, because plus and minus 0 are the same number, essentially, so we're going to end up with one root, or it says two equal roots, because remember, the term of adding 0 and subtracting 0 will result in the same root. So basically, they are equivalent to each other, right? One of the roots is the one where you add 0, and the other root is the one where you subtract 0, but they're essentially the same root, so we call them two equal roots. Finally, what if k was less than 0? Well, I'm not even going to bother writing it, because if k was less than 0, we would end up having a negative number under a square root, which we all know, if you don't factor in complex numbers, is impossible. You can't get a square root of a negative number without introducing complex numbers or i's into the mix. If you do introduce i's, then you're going to end up with two different answers, right? Because if this k underneath here is less than 0, it's not 0, so we're going to end up with a plus whatever imaginary complex number we get in here, or we're going to end up with a minus whatever imaginary or complex number we get in here. So it's still going to be true roots, but they're not going to be real. They're going to be complex. Or you could say, if you ignore the fact that those complex roots exist and say, okay, we just care about real roots, since we're not going to get a real number out of this answer, we're just going to say 0 real roots, right? That's the reason why this works, because it all depends on what number is under the square root. This number under the square root is our discriminant. It helps us identify, without solving the equation, right? Without even solving this equation and getting to this point, we are able to find out whether or not this equation actually has roots, right? Because if we check the discriminant, we are able to determine whether or not an equation has real or complex roots, or how many roots it has, right? Because a quadratic can have a max of 2 and a minimum of 0, right? In terms of real roots, right? So this helps us identify whether or not an equation has real roots or not, without even solving the equation itself. That's why it's so useful, right? And this is the reason why you should have memorized these conditions, because it's in the formula. The quadratic formula already, which is usually given in your formula table if you're taking maths at high school level, you should be given a formula booklet with this particular formula already in it. So this formula already tells you what conditions need to be met for an equation to have two different real roots. This has to be positive, not 0, because if it were 0, this would be those two roots would be the same, right? If it was less than 0, then we just have no real roots or two complex roots, right? You don't need to memorize these cases. You just have to memorize or just note the formula and all the different parts of the formula, right? So that was just a short little test that turned out to be 20 minutes. It's just going to be unedited because, you know, I needed, it's just a short test to see the feedback on like what I can do to improve on maybe the presentation style and maybe how I present certain things. So let me know in the comments, if you're watching this, let me know in the comments what I can do to improve, or maybe other topics you might want to see on this channel. And that's it. Thanks.